So the central thing about this chapter, kinetics, is that in order to have reactions between two or more reactants, those reactants must collide, and then they can then combine or change each other. So for example, for A to react with B to form C, A and B must collide, and once they do that, they can combine and form this new compound. Now, it turns out that not all collisions, though, will result in reaction. In fact, in order to react, your reactants must have a certain initial kinetic energy, which can be turned into the potential energy needed to react. But additionally, those reactants must collide with a certain orientation or angle, and also hit at the right kind of areas of those particles. And so very few collisions actually result in reaction. Now, it turns out then that this rate of reaction, which is the amount of change of our reactants or products versus time, is dependent upon the concentration of our reactants. If we have more reactants, then we can expect that we'll have a higher rate of that reactant reacting. So for example, in order for A to react with B, they have to collide together, and so if you double the concentration of A, you might expect that you can double the rate, because A's will be colliding with B's twice as often. Okay, so we see that there's this central relationship between the reactant concentrations and the rates of reaction. This applies also if we have just decompositions or spontaneous or seemingly spontaneous changes of one reactant particle into one product. For example, A turns into B. It doesn't need to collide with anything, yet its concentration still is centrally related to the rate of reaction. For example, we can see that we can start with, say, 40 particles of A and 0 particles of B. And over time, as A seemingly spontaneously turns into B, we see that its concentration falls. But as the concentration of A falls, the rate of turning into B falls as well. Being that there's less A, there's less reacting of A into B. Now, this rate of reaction can be defined as the slope here, or the change in the number of particles versus the change in time. So rise over run. Kind of demonstrating all this, instead of with the graph, just by talking about the number of certain particles, we might say that at the first moment we have 40 A's and 0 B's, and at the second moment, maybe 10 seconds later, we have 30 A's and 10 B's. And then 20 seconds in, we have 22 A's and 18 B's. We can define the rate by discussing the average rate. This is the change in the concentration of reactant or product versus time, where time is not instantaneous but a given amount. So for example, the change in concentration of A versus time for those first 10 seconds. The change in the concentration of A, or the change in the number of A's, was, we started with 40 A's and we turned into 30 A's, so 40, and then 30. So there was a change in 10 A's. And the change in time, we started at 0 seconds and then we ended at 10 seconds. So 10 seconds minus 0 seconds, that's a total of 10 seconds changed. And so we changed 10 A's over 10 seconds, so that was a rate of 1.0 A lost per second. And then we can see that this average rate differed later on, where we lost, going from 30 to 22, 8 A's, and going from 10 to 20 seconds, we had 10 seconds changed. We had 8 A's per 10 seconds, or 0.8 A's per second. We can see that that rate of reaction is dependent upon the time. Over time, that rate falls because we have less A, and we also see that as we have less A, we have a lower rate. Now, this average rate is not the best way of describing the rate of reaction because it is dependent upon how you measure it. Now we saw that if we measure this rate in intervals of 10 seconds, we had a rate of 1.0, then 8.8, then 0.6, then 0.4. But if we discussed a larger interval of time, say instead of 10 seconds, 40 seconds, then we can actually see that this average rate was 0.7, which is not actually an average of 1.0, 0.8, 0.6, and 0.4. Yes, average rate is not the best way to describe the rate of reaction. Instead, we like to discuss instantaneous rate. Now, instantaneous rate is discussing the change in the concentration of a reactant or product versus time over just one instant. Now, you've perhaps seen in calculus that it's better than, say, discussing a large interval of time and finding the change over that time. It's better to get into smaller and smaller pieces until you get to an infinitesimally small change in time and concentration at that instant. And you learned that you could find this instantaneous rate by finding the slope. Yes, the slope is equal to rise over run, which is equal to that change in the concentration of A versus time. And so you'll sometimes be creating graphs to find that instantaneous rate. Now, notably, for this reactant, this instantaneous rate is the negative of the slope, because though our reactant is falling in concentration versus time, we know that the rate must be positive, and so take the negative of that. Whereas you would take the slope of the product without reversing the sign of it in order to find the rate. So here for the product, we have a positive slope as we have a positive rate. Here for our reaction, we have a negative slope as we have a negative rate. Almost finishing up here, we saw that at time 0 seconds, when we had 40 A's, our rate of reaction was about 1.0. Whereas later at 20 seconds, where we had about half as many A's, we had about half as much rate. In fact, you can see that as you have the concentration of A, you have the rate, or about. And more effectively in actual experiments, you'll see that. And so you can see that the concentration of a reactant and the rate of the reactant in this reaction are directly proportional. They are directly proportional. In fact, you can create an equation describing this directly proportional relationship. For example, if you made A go up in this equation, you would make rate go up by the same degree. In this directly proportional relationship, we have K, a rate constant, and this reaction is our, or equation is our rate law, which we'll spend a lot of time with. Go ahead and watch the next video on rate law. Thank you for watching.